Okay, so we're on module 11, y'all, and keep in mind that next week is spring break, okay? So you have the week off, and when you come back, we'll pick back up on 11B, okay? All right, so don't come next week. All right, we're lab 24. Do we have our pages open to the right place?
Yes.
Lab 24?
87.
87. All right, so have we talked about the 4 fundamental forces of nature?
Yes.
Okay. Remember, my confusion is in
Yeah.
general science, we did that too, remember? Yeah, so I'm getting this class mixed up with general science. Okay, so our forces are gravity, the weak force, electromagnetism, and the strong force. Which one's the strongest?
The strong force.
Thank you. Which one's the
No,
weakest? Don't fall for it.
gravity.
I was going to say don't fall for it. Yeah, it's not the weak force. It's
I was about
gravity.
to say weak.
I think weak force is probably the second strongest one. Yeah. Oh no, I guess electromagnetism is. Look, they have them in order here.
That's what they use for like trains, like those electric trains.
Yes, sure enough, right. So we're going to be talking about electromagnetism today, and looking at static electricity and
The
things like
range
that.
is infinity
For what?
for electromagnetic.
Oh yeah, right. Well, you talking about this?
Same with gravity.
No, it says the range, then it goes infinity.
Oh, infinity. Okay.
Same with
Is this-
gravity.
Yeah. Yeah, gravity right there. How about that? Whereas the weak force and the strong force are happening inside a nucleus of an atom, you know, in a very small space. Yeah. So, all right. So we're going to start with this guy. This is Sir Humphrey Davy. So it turns out that all these scientists came along to figure this thing out about electromagnetism. And the interesting thing is that they all were very competitive with one another and kind of sort of hated each other, okay, because they were so competitive. So this is Humphrey Davy. He was a chemist and an inventor. He isolated, by using electricity, the series of elements for the first time, including potassium and sodium in 1807, calcium, strontium, barium, magnesium, and boron the following year, as well as discovering the elemental nature of chlorine and iodine. He also studied the forces involved in these separations, inventing the new field of electrochemistry. So he was very interested in chemistry, but he started seeing how electricity was helping to pull those things apart. Because we're going to get to it here in just a minute. In chemistry, when we have our elements and our atoms, those atoms can take on an electrical charge. And when they take on an electrical charge, they're called an ion. And when that happens, they can be used for special applications during chemical procedures. The next guy is called Michael Faraday, British. Davy was British, and so was Michael Faraday. One of the greatest scientists, contributing significantly to the fields of electromagnetism and electrochemistry. I think he and Davy were kind of rivals, if you will. But he's the one who's credited with, because he was more interested in the electricity part of it than the chemistry part of it, even though he did chemistry stuff as well, he was very interested in this part. And what he put together was that electricity and magnetism were two parts of the same thing. Didn't we draw the thing, didn't we try to draw the electricity and magnetism kind of thing? Was it last
Yeah.
week? Yeah. So he's the guy that really put those things together and discovered that. We talked about a couple of guys last time. We're going to watch a little part here kind of from a movie, all right, showing when this is not as long as it shows
You have the
here.
popcorn?
Faraday was different from anybody else. He had a flair for understanding his experiments, for understanding what was really going on inside them.
By methodically placing a compass all around an electrified wire, Faraday started to notice a pattern.
Remember Orsted did that.
What everyone else at the time had been taught was that forces travel in straight lines. Faraday was different. Faraday imagined that invisible lines of force flowed around an electric wire. And then he imagined that a magnet had similar lines emerging from it, and that those lines would get caught up in this flow. It was a bit like a flag in a wind.
But Faraday's great leap of imagination was to turn this experiment on its head. Instead of an electrified wire moving a compass needle, he wondered if he could get a static magnet to move a wire.
I've never seen you like this, Faraday. You look like a happy child. I'm shaking, Newman.
Use it, Charlie.
Underneath, I'm shaking. You see, John? You see?
Yes.
Max is talking
good then.
Inside that cup is mercury.
This is the experiment of the century. It's the invention of the electric motor. Scale up the magnets and the wires, make them really big. Attach heavy weights to them, and they'll be dragged along. But almost more importantly, he's inventing a new kind of physics here.
Although he didn't realize it at the time, Faraday had also just demonstrated an overarching principle. The chemicals in the battery had been transformed into electricity in the wire, which had combined with the magnet to produce motion. Behind all these various forces, there was a common energy.
Does the
Magnet did not move. Magnet caused that magnetic field. Oh, this must be Davy.
A couple of months earlier, Davy had been elected president of the Royal Society, which was the elite body of English science. But then he saw this great discovery published in the Quarterly Journal of Science. I don't know if he was envious, but he certainly saw that this young man who had been his assistant, this mere blacksmith's son, had come up with one of the greatest discoveries of the Victorian era.
We're in the Victorian? We're in the Victorian era?
Yes. So 8.
Davy accuses Faraday of plagiarizing similar work from another eminent British scientist, William Wollaston.
So, Faraday, what does Wollaston make of all this?
He's written to me and assures me that he's taken no offense. And he acknowledges that what I published was entirely my own work.
Right. Davy is just being an ass.
But will Davy now retract his allegation?
Sadly, no. In fact, he's still vehemently opposed to you being elected a member of the Society.
Really? And what do you think?
Faraday, my dear boy, you have my vote.
And mine. And I believe you even have one.
Okay, so that's just showing a little bit of the politics behind that's going on, where Davy was a little jealous of what Faraday. What Faraday did was a pretty amazing thing. So he has this massive idea of electromagnetism. So that magnet was sitting in there still, and just the field around it was pushing on that wire, causing it. It showed the magnetic field. And seeing that, he said, wow, here's what we can do. We can turn it into motion, and if I have motion, I have energy. If I have energy, I can do stuff, right? Okay. Next comes James Clerk Maxwell. We mentioned him last time a little bit. James Clerk Maxwell is often thought of as the father of modern physics. Okay, so what did Maxwell do? Sadly, he's very, very, very smart guy. Also a strong believer. We saw that last week, right? He was a strong believer. He put mathematical equations with the concept of electricity and magnetism and showing them to be the same force. Here's all his math back here, which I don't understand at all.
It's hard to see because of the.
Yeah, I didn't mean for you to see it necessarily. Just lots of math. All right, so he put in mathematical equations to show the relationship between them. So here he is, all this stuff floating through his head, all these mathematical equations.
Is that Chinese?
Looks like it, doesn't it? It has a question mark after it.
Korean?
Yes.
Is he the reason why we do math and science?
Not really,
No.
but he did. All science can have math brought into it, and when that happens, I'm always like, bummer, man. Yeah. So, but he is one of the reasons.
Well, science and math work together.
They definitely do. All right. Let's see what this is. Continuing the story.
Long before the 19th century, scientists had computed the speed of light, but no one knew what light actually was. Back in England, a man we've already met was willing to make an educated guess. After Sir Humphrey Davy's death, Michael Faraday became Professor Faraday, one of the most important experimenters in the world. The scientific establishment still found it hard to accept that electricity and magnetism were just two aspects of the same phenomenon, which Faraday called electromagnetism. But now, he has an even more outrageous proposal for his audience.
Invisible lines.
It can emanate from electricity in a wire, from a magnet, or even from the sun. For it is my contention that light itself is just one form of these vibrating lines of electromagnetism.
For 15 years, Faraday struggled to convince the skeptics that light was an electromagnetic wave, but he lacked the advanced mathematics to back up his idea.
Who's gonna help him?
Eventually, someone came to his rescue.
Math guy.
Professor James Clerk Maxwell believed in Faraday's far-sighted vision, and he had the mathematical skill to prove it. Maxwell and the aging Faraday became close friends.
James, forgive me. A word of advice. Don't get old. Michael, how are you? I'm fine. Memory isn't too good. Well, I thought you might like to see what I've just published. Oh, yes. Yes. Splendid. So your results show that when electricity flows along a wire, what it actually does is create a little bit of magnetism. And as that magnetic charge moves, it creates a little piece of electricity. Electricity and magnetism are interwoven, like a never-ending braid. So it is always pulsing forward. It's wonderful. Wonderful. Michael, there's something very crucial in maths. This electricity producing magnetism and magnetism producing electricity can only ever happen at a very particular speed. The equations are very clear about it. They come up with just one number. 670 million miles per hour. I'm not sure. It's the speed of light. That is the speed of light. You were right all along. Light is an electromagnetic wave.
Maxwell had proven Faraday right. Electricity and magnetism are just two aspects of a deeper unity. A force now called electromagnetism, which travels at 670 million miles per hour. In its visible form, it is nothing other than light itself.
All right, there we
Is
go.
that from a movie?
Some sort of special show. I'm not sure what it was. Yeah,
A documentary.
some documentary.
It looks like it.
Yeah. All right, 2 facts about the electromagnetic force that we know now. Okay, this is going in your book. Ready?
It is.
Opposite. Oh, it's not? Okay, then hold on just a second. Opposite charges attract, positive and negative, and like charges repel.
Just look how it goes in there.
It doesn't go in there. You're right. So we're gonna try something like this during lab time.
The
Okay.
balloons?
Yeah,
Are they wire
to see,
balloons or?
to see, get them to repel.
Oh,
Ow.
are they wire balloons?
No.
I'm
no.
gonna put
Now here we go.
magnesium.
3 principles about electrical charges. Number 1, all electrical charges attract or repel each other. Like charges repel, opposite charges attract. That's going in box number 1. Attraction or repulsion. And we already know that like charges repel and opposite charges attract, yes?
Yes.
Number 2, the force between charged objects is directly proportional to the amount of electrical charge on each object. It's directly proportional to the amount. How big is the electrical charge? And then 3, the force between charged objects is inversely proportional to the square of the distance between 2 objects.
I'm still on one.
It's okay. I'll give you time to write this down. I know, I wish this were fill in the blank time, but I guess it's not. Also, we didn't spend as much time, I wish we had, talking about gravity.
Gravity's cool.
Gravity has some interesting principles as well. Yeah, so this might be a good time to practice not writing every single word. When you get to college someday, the professor's not going to wait. So maybe figure out how to shorthand it, right? Find the bullet points and write the bullet points down. Notice I do have a star up here. The star means important. It's important. Question?
I skip the words and I fill them in. I skip
Oh,
the words I
smart.
can remember and I fill them in after.
That's pretty smart. All right, as soon as you're finished writing, we'll talk about what these words mean.
Michael Faraday also considered Faraday cage, right?
It's certainly named after him. I think he did. Yeah, yeah. So, and that was electricity as well. He was a pretty brilliant guy. Yeah. But the people laughed at him. I just find that so interesting. We look back now; he was totally right. You got to be courageous to step outside the box of, orthodoxy.
Because someday it'll be important.
Somebody might say, "Wait, he was right all along." Yeah.
Right.
So it's good also not to just assume somebody's wrong just because what they're saying sounds outrageous or outlandish or fantastic. You
Because
say, "What? Yes, we'll
Some
think
people
about it."
don't like it.
Yeah. Well, so I'm sure some of the people, if they had been his rivals, maybe were hoping he was wrong and wanted to make fun of it. All right. So let's see what this says. Number one's easy, right? Electrical charges attract or repel. We just learned that principle. Like charges repel, opposite charges attract. And since we already talked about the strong force, remember it has to be strong because those are all positively charged protons in there. And if they're positively charged, they should be pushing away from each other. But the strong force holds them together with probably something we're calling gluons. I always say they're glued on there, right? There's really something holding on to them. We don't know exactly. So that one we understand. Now, the force between charged objects is directly proportional to the amount the electrical charge on each object. So think about it this way. If I have, let's say I have a ball of energy right here and it has a very, very large charge to it. Okay, and I have another one over here that's the opposite charge, and they're going to be attracted to each other. If it's also big, those big charges will be attracted to each other even more, with more force. You get it? Yeah. But if they're really tiny and they're like this, it's not going to be as big an attraction. You know this think about magnets once again. We have strong magnets and we have not very strong magnets, right? Yeah. So think about if we have strong charges, they're going to be attracted more to each other, yes? That's directly proportional to how big the charge is. All right, so boom, they'll come together. Number 3, the force between the charged objects is inversely proportional to the distance. But not just the distance, the square root of the distance of them. The farther apart they are, the less attracted they'll be to each other. Yes?
Yes.
Okay, that totally makes sense, doesn't it? So my next slide isn't going to make much sense since we didn't talk about gravity very much, because I say sound familiar. It turns out the principle of gravity is exactly the same. In other words, the mass, remember gravity has to do with mass, right? Yeah. The larger the mass, the stronger the pull of gravity, yes?
Yes.
Jupiter, right, is the biggest planet. It's got the biggest amount of gravity on it, yes.
So like say the sun was a planet, right? How strong, would you be able to stand up if the sun was a planet? No, it's mass. It's more massive than Jupiter, right? So it's massive. So let's see, so we have a massive thing like that, and the bigger its mass is, the more it's going to attract something toward it. Just like the thing I just said before, right? Yeah. Just like the charge. Think of the mass now. If I have large masses, they're going to be directly proportional to how big they are, how well they'll be attracted to one another, yes?
Yes.
Meanwhile, the distance apart will get less and less. The gravitational pull will be less and less based on the square of the inverse proportionality of distance.
That's why, like from the sun, the farther things apart are the more likely they can break away.
Exactly, right. So here I just described to you what gravity was, and I just basically used the same words as describing to you what electromagnetism is. Isn't that weird? So when Mr. Faraday gets made fun of for saying that light is just part of this spectrum, well, it's very possible gravity may be a part of this spectrum too. Right? Of all the forces, the four fundamental forces, they're all in this electromagnetic spectrum. We just don't know how gravity fits in right now. We don't know how gravity does what it does. We know what it does, and it's very predictable what it does. How it does it, not exactly sure. There might be particles called gravitons. And I had my students in the previous years, we'd study gravity, and like say you and me, Sudie, and I'd throw a ball to you like this, and you catch it, and you throw it back to me. But then we get farther and farther apart, and there'd be more of a chance of us not catching the ball, because it's less accurate the farther and farther apart we are.
Unless you're a quarterback.
Unless you're, Tom Brady, right? But then I couldn't catch it. So I just find that fascinating, that gravity kind of fits in there too. Okay, so now the next part of this thing is possibly not in your book at all. So forgive me if this is not, okay, just ignore that. Page 290, just ignore that. That's not going to be right. But it says in your book, math from the book. Doesn't it say something about math?
Yes, science and math.
Science and math. Discuss science and math. All right, so here we go.
There we go.
Two charged particles are placed 16 centimeters from each other, and the resulting force is measured. Don't know how. The charge on object number 1 is then halved, cut in half, and the charge on object number 2 is divided by 4.
So it's cut in 4.
Yeah. So that's going to make their draw to each other less, correct? Okay. The distance between the objects is reduced, they're brought closer together, to 4 centimeters, from 16 down to 4. How does the new force compare to the old force? Has anybody read their part of their module yet? Have you started reading it? Anyone?
For 12?
Did you have problems like this?
Yes.
You did. So this is, this does apply to our lecture today. Okay, because I meant to go back and check it and put the right page number in, and I totally forgot. Yes?
I would think that the new force is the same as the old force.
Okay. Erebus is saying it's going to be the same. All I know is the next slide has lots of words on it. That's all I know. So let's go through it. Here we go. The electromagnetic force is directly proportional to the charge of each object, right? That's principle number 2. Directly proportional. All right. Thus, when one object is cut in half, the EM force is also cut in half. Right?
So 8?
It wasn't 16. It was, I gotta go back.
16 centimeters.
It was, what was the charge? Oh, it just says it was halved. It doesn't tell us what the charge is. Okay. All right. The electromagnetic force is inversely proportional to the square of the distance between the charges, the square of the distance, square root of this, and so we're going to say the distance has changed from 16 to 4, so it was divided by 4. When the distance is divided by 4, the force is multiplied by 4 squared, okay, which is 16. All right, so the force was divided by 2, divided again by 4, then multiplied by 16. Dividing by 2 and 4 is like dividing by 8. Then we multiply by 16, so the net result is a multiplication by 2. Everybody with me?
No.
No. I don't blame you.
I
The
have to
new
read it
force
again
is
like
therefore
3 times.
twice as strong as the old force. I just copied this straight out of the book, y'all, because I'm sitting there going, okay, yeah.
This is a nice calculator.
If you say
I
so.
need more time to calculate this.
Yes, so here's the deal. You're going to have some practice problems like this, apparently, in your book. This
is in the book?
It should be. This should be one
Where?
called an example. Like it's actually in the book, not a OYO, not a practice problem, not a study guide problem.
So
It
it's
should
not
be
OYO
like while
222?
you're, right, it just should be, oh, that is a OYO, isn't it? Okay. I don't think it is though. All right. So here's what I'll tell you. The fact that we didn't put a bunch of these problems in your book to do during class right now indicates to me we're not going to ask very many questions about this.
Who's we?
We being the ODA staff. Remember, this is brand new. We're trying this thing out brand new. Used to in the old book, I had things you had a box, you had to write all this down, and we don't have it this time. So I'm guessing it's not going to be. Now, are you telling me you don't have to study it? You do have to study it. Yes, Olivia.
Is it gonna be in the quiz still?
Well, I don't know. I haven't seen the quiz. I haven't written the quiz.
Ask me next week, maybe.
But I will check the quiz if I remember, and make sure there's nothing too complicated on the quiz. Okay. All right. Erebus has her book out. Is there something called 12.2?
The OYO 12.2 is something about not electrics.
There's that. I've done this problem.
The one I said you did the exact problem?
Yes, I've done this problem.
Okay.
The answer's 36.
The answer's 36?
Yes, ma'am.
I thought it was 2.
No.
The new force is therefore twice as strong as the old
So
force.
it says so the net result is multiplication by 2. So you multiply 2 by 16.
Oh.
36.
So I should have had something else to finish this problem. I don't. Okay. Anyway,
Where did you do it?
I don't know where it is in the new book, but Sudi says he saw it.
I've done it.
And he's not using the old book, or anything. Not an old book. Okay, I got that problem written down from the old book. Okay, moving on. What is a photon? A photon is a small package of light, quote unquote, that acts like a particle. So you're writing down package of. A small package of light that acts like a particle. Remember, we covered that quite a bit last time.
Where's the writing down package?
Package of, yeah.
Of's already there.
Oh, it is, so package. How do they work? The exchange of photons can generate an electrical force. So, just like I was saying earlier that if gravitons are real, and I'm tossing a ball between, you and me, right, back and forth, so there may be a particle of light that's traveling back and forth. And observing that the farther apart I get, inverse square of the distance, that's all coming in there, same deal. And that particle of light is called a photon, and it happens, well, all the particles, including gravity, happen to be traveling at the speed of light. That's the secret of all of it, right? So we see it here, we see this sort of white wave packet thing, and what it can do is it can cause a change, something to change its direction. All right, and I'm gonna bring this around in a second and show you it's kind of one of those wow moments that comes along here. All right, so a photon, how do they work? Well, nobody really knows, but we think there's an interaction of charged particles causing the photons to be exchanged, just like I'm throwing a ball back and forth, okay? Exchanging particles. The closer together we are, then the more accurate we are, right? The quicker we are. Okay, so the closer the distance of the objects, the more photons are exchanged, and the higher the electromagnetic force. Remember, they're little packets of waves. That's how we kind of draw them right there. So this is going to blow your mind. If this is the case, you know how when you take a magnet and you can push it to another magnet and make the magnet move away from that magnet? Didn't we do that?
Yes.
Remember how we can do that? Well, maybe it's a photon that's doing that. That's the charge. That's the thing in the magnet that's doing it. Crazy, huh? So under particle theory of force, a photon transfers momentum directly to a charged particle that's being moved. Let's say it's another magnet being moved away. So what comes in there is a photon. That's crazy. John Mark, put the phone away. All right, so action on a distance is what that was. So next question is, what is an ion? We know what an atom is, right? An atom has a nucleus, and what's inside the nucleus?
Charged particles.
Nucleus.
Called what's in the nucleus?
Neutrons.
Atoms.
Protons is what I'm looking for. Neutrons, yes, probably, right? Atom is the whole thing. What's spinning around it in orbit? Electrons. Okay.
Cool.
Now, when we're talking about ions, a lot of time what we're looking at is chemistry. Okay, so what I need you to know about chemistry is about dealing with electrons. The electrons spinning around in the cloud outside the nucleus, manipulating those, changing those, exchanging those, that kind of thing. That's chemistry. Okay? We don't ever mess with, okay, not ever. We don't mess with the nucleus in chemistry. The nucleus, protons and neutrons, that's nuclear physics. It's a different science. Okay? The only time in chemistry that we deal with the nucleus is if we have an atom that is radioactive. And that means the nucleus is falling apart all by itself. It's unstable, it's falling apart. Okay? That's the only time we see that in chemistry. All right, so what we deal with mostly, though, are the electrons, moving around, exchanging them, sharing them, this kind of thing. And so here we happen to have sodium. Sodium has 11 protons, and it has 11 electrons. Okay, that's number 11 on the chart, right? But sometimes it's got this one out there in the outer shell that's just all by itself, so a lot of times it'll just give away that electron. It'll give it oftentimes to chlorine. sodium chloride, right? It'll give it away to chlorine.
Yes.
Alright, so we end up with 11 protons because remember in chemistry we don't mess with the nucleus. You can't mess with the nucleus, it's against the law. Leave the nucleus alone. Protons are untouchable. But I've got only 10 electrons. So that means I have an unbalanced force. I have more positive charges than negative charges. So therefore this particle right here takes on a sodium +1. It's got one more proton than it has electrons. You get it? One more positive charge than it has negative charge. That's called an ion. An ion is what takes on a charge. The chlorine will have taken on a negative charge, so it'll be Cl negative ion.
There's to be an anion.
Yep. They're called cations and anions. So if we see an atom, looks here, sodium again. See that one electron sitting out there all by itself? It gives it away. Now it doesn't have it, and it takes on a positive charge. So it's sodium plus, or a sodium ion, a sodium cation. Okay? So why am I telling you that? Because it's not in your book at all. Because we need to understand that for the next series of blanks that we're about to fill in. And I might advise the ODA faculty to include this in here so we understand what ions are. Okay? So here's what we're going to talk about. So we're talking about light. Yeah? Okay? So when atoms lose electrons, they become positively charged. It's kind of where you think you lose something, it's positive, right? Because we have lost, what have we lost?
A negative.
A negative charge. So therefore it takes on a positive charge. All right. When they gain electrons, they become negatively charged. That makes a little more sense. I'm gaining something here. Well, it doesn't because you're gaining, right? But gain is negative here in this case. They're gaining a negative charge. Electrically charged particles affect other charged particles, creating an electrical field because negative and positive will be attractive to one another. Positive and positive will be repellent to one another. And we have the same thing going on that we have in magnets and we have in electricity. We have the same thing going on in chemistry. I put a negative and a positive ion together. They stick together. It's called an ionic bond. Pretty cool. Sodium chloride. They stick together. They're like magnets. Number 4, static electricity occurs when charges build up within or upon the surface of an object. So what's going to build up is charges. Typically a negative charge. So typically what builds up on the surface of something is an electron. And we used my little electron generating stick, right? And we did that whole thing, right?
Yeah.
Yeah, we've done that in this class. All right, do you have your blanks filled in?
Yep.
Everyone? Okay. All right, so that brings us to static electricity. Okay, so we see right here, we have the balloon, right? The hair sticking up like that. Today's a really, really low pressure day, so we're going to have a little more trouble generating some electrons today. Yes?
If you ever like in a field and it's like cloudy and your hair starts sticking up, you need to like,
maybe you might want to run.
You need to get somewhere like that.
Yeah, you might have some lightning coming your way.
Yeah.
All right, so here's our, speaking of that, right? We can do that. You had that happen before where you have a static shock from something like a doorknob, right?
Oh, yeah.
Jumping on the trampoline and you come out, you touch somebody, touch the side trampoline, right? And you get shocked.
Oh, that sucks.
Yeah.
It does.
Sometimes
That's why
it
I
does.
always
Have you
jump
guys on
off.
All right, the way that
On
charges
the
build up, okay? First one is friction.
Friction.
Friction's a way that charges build up. Write it down.
yeah.
Oh, you're over now? It was already there, man?
Is that where like the sparks come out whenever like you stop like say like you stop?
Yeah, you,
Like a
it's,
skateboard or
you
something
know,
like that.
yeah, so like you've been generating them for some,
Yeah.
you're moving around, right? And so like if I move around like on, especially on something that's gonna be a little, you know, I might gain some electrons and get that shot. Didn't we watch the video with the guy gained all the electrons and got shocked? Did we not watch that video?
No.
Oh, that's a good one. I should put that one in there. It was pretty good because he's like, "Ee," you know, and it's almost like a static electric shock is like painful. It's not really, right? You
Yeah.
might do that and say, "Whoa," but it doesn't burn you.
You should have the clip from Home Alone 2 when he grabs the sink and he just
Who grabs the sink?
the bandit in Home Alone 2 whenever they
Oh, okay. That would be a good, what do you call that little GIF, GIF, whatever. The next one is called
that was
conduction. This is going to have a very specific definition here in just a minute. And the last one is induction. So friction, conduction, and induction. And friction we already know about, right? So we're going to see here, to charge by friction, two items are rubbed together and one transfers electrons to the other one. So we see right there, the balloon is attracting this girl's hair.
You wouldn't happen to have any balloons, would you?
I do, that's part of our lab today. We're gonna use a specific little, we're gonna do one of these conduction
Do I
induction
get
things.
to take one?
They're pretty small, but yeah.
That'll work.
Let's think about charging objects, okay. Charging by conduction is charging an object by allowing it to come into contact with another charged object. Right? That's conduction. Charging by induction is an object is charged without direct contact between the object and a charge. They don't actually touch. They just come really close. They come really close. All right, so these are two ways of charging something, but two different ways. One you're touching it, and one you're not.
Like the clip that they saw with the doorknob is now
Not touching it.
It wasn't touching it.
Right. Okay, so here's that conduction when they're touching it like this. Okay, charging an object by allowing it to come into contact with an object that already has a charge. Okay, so I have this charge right here. This is before, this is after. Okay, and I'm touching a ball that has no charge, like a metal ball right here. And it's going to confer that charge over to the metal ball. And so they're both negatively charged right there because it touched it to it. The object will take on the same charge as the charging object. So I brought in something negative and it charged that thing into a negative state. Okay?
They repel each other.
Yeah. And you take it away and you just have a charged object. In this case, negatively charged object. Okay. Now induction's a little different. Charging an object without direct contact between the object and a charge, the object gets the opposite charge. Okay, so here I can see right here I bring in, I bring it really, really close to something, and so the little wand here in this second picture here, you can see the little wand has positive charge. It's hard for you to see because it's kind of small, and I'm going to bring it right close to this generator ball right here, and it's going to cause all the negatives to be attracted to the positives, pulling all the negatives to one side of the ball, okay, and all the positives are going to end up over there, and then right here the electrons, somebody touches it and grounds it out and takes all those positive charges out, leaving the sphere negatively charged. So the charging wand was positive, the sphere ultimately was negatively charged. So it takes on the opposite charge of what you were charging it with because it comes close to it. Yes?
Miss Catherine, so in dry weather, when I pet my cat, her hair sticks up before I even touch it.
Yeah.
Like,
Cats are pretty infamous for that, or famous. All right, so here it is, a negative. This is showing it a little differently here where the negative rod comes up. All the positives are just flowing through the ball. They're not coming out of the ball. They're staying on the ball, okay? And it's flowing to this opposite charge right here, causing the positives to collect on one side. And the negative charge is over here. This one to me works better because it makes more sense for this person to touch it and take the negative charges out of there. Let's see. The movement of electrons is merely a reaction to the presence of this charge because like charges repel. Once touched to the ground, the electrons leave the sphere. When the tube is moved away, there are overall positive charge on the sphere. Okay, so the first one was showing a negative charge. Oh, here, I've got this little thing to watch. Okay, we have here, this is induction right here. We have two marbles or whatever, and here, I like this because it shows them on separate pieces right here. So notice this is going to be opposite charge of that, and now we have two charged particles that are going to be attracted to one another because like charges, opposite charges attract, and then they can redistribute their charges. So you get it? Yes.
Have you ever tried to get a magnet and put the wrong sides together?
Oh sure.
It's super hard. It's
yeah, they're repelling each other big time. So that's called levitation. It can cause a levitation, and I think that's how some magic tricks might be done.
I can be Iron Man.
Yeah. All right.
Oh, I've seen that.
Now this is another way of showing. Yeah, this thing right here is called an electroscope, and so I have a couple of electroscopes here today. And this is charging by induction because we have a positively charged rod and it's charging the opposite of it. And it didn't quite touch it, right? So I think we're gonna be working mostly with induction today. All right. Here you can see once again the negatives coming, and look what it does to these little metal pieces hanging down here. It's causing those to move. All right, so we're gonna do that in an electroscope today. All right, so typically the lecture would end here, and we'd talk about this, and but we're not ending it here. It's kind of a little bit awkward that they move on to basically next week's, which isn't next week because we have spring break next week, so week after next. Electrical circuits. So we're going to go ahead and fill those blanks in, and then we'll just review it next time. And we'll do a lab with electrical currents the next time we're together, okay?
Oh, I did that in engineering.
Yeah, it's good. It's fun to do
We
that.
put like
We
we
can
put
do
like
this.
we put like
You made
copper and
potato
zinc
Oh, make a battery?
into oranges.
Mhm.
And we turned on like lights and stuff like
Very
that.
cool.
And read the frequencies and it was like
Oh, that's very nice, yeah.
pretty fun.
I was gonna say, can we do this next week then, since it's not part of our lab today?
We'll do it next lab, which is 2 weeks from today, because we have spring break next week.
We might even talk about it this week.
What?
Why are we doing the notes this week?
I don't know. I told you it was awkward, and I normally would end before this. I didn't do it. I didn't write the book. All right. I guess maybe it's just too much for 1 week next time we're together. So electrical circuits. Here we go. Electrical circuits provide electricity. In an electrical circuit, electrons flow through a wire. The rating system for electrical, it should have a word there, electricity is volts. The rating system for electrical.
I have the rating system for electrical charge uses the term volts.
Okay, I'm missing some words in mine, obviously. So that word is volts you're writing in there. Okay, that's just the unit we're using. This is determined by electrical current, the amount of charge that travels past a fixed point in an electrical current per second. Okay? So what is current? The amount of charge traveling past a fixed point in an electrical circuit per second. That is called the current. Good? All right. So you need to draw this. You're drawing this in your box. We will cover this again next time we get together. We'll review it. We will have been off a whole week. So when you're working with circuits, you hear the word circle. We have to make a circle. So this picture right here is showing the picture of something known as an open circuit. An open circuit doesn't allow any electricity to flow through it. For instance, the lights on this side of the room over here, the switch over there has been turned off and opened the circuit. This circuit is closed, allowing the electricity to flow.
If it's open, the electricity would just flow out. So
It just
doesn't flow at
stops.
all.
It just stops. It doesn't flow at all.
Yeah, but
I mean, it doesn't even go anywhere. It just doesn't do anything. It doesn't flow.
if it was flowing, it would have to flow out. That's why it stops.
Yeah, it stops. It just, the battery's not utilizing any power.
Some people think it'd be the other way.
I know, it sounds almost a little backward, but when you look at a circuit like that, you can see the reason why. So I'm guessing y'all are drawing an open circuit then, yeah?
Yep.
Okay. You might want to write above it, open circuit. No power. Nope, it's powerless.
So is this
Well-
what your lights look like every time you have like a blackout or anything like that?
What?
Like say you have like a blackout.
You're talking about you personally, in your brain?
No, like in like your lights.
Oh, we're talking about electricity.
No brain.
So when we have a blackout, I don't always call it that. Okay, when we lose electricity, yeah, the circuit's been open somewhere. Yeah, probably, sometimes it'll be a down power line, and the power line gets broken, and yeah, can't come to your house at all. Sometimes it's in your own house. Like, for instance, you'll have a circuit gets tripped,
Mm-hmm.
called, a blown circuit. And most of it has to do with if you're overloading the circuit at that moment, like you're running your hair dryer and your iron and your microwave
See,
all at the same time,
that
and
was
your
wrong
things
with my
that take a
grandma's
lot of
kitchen.
power.
She would have the mini stove on. Well, she has to plug everything in. She has a small kitchen. She was like in an apartment we made.
Okay.
So she had to plug everything in, like a mini, like stove top, and then like a griddle, and then like her microwave and her coffee, and it shuts everything off.
Almost always, the microwave takes a lot of power, and so therefore, if you got a bunch of stuff plugged in and going, and all of a sudden you push go on the microwave, it'll blow that. And it's not wrecking anything. In fact, it's a safety mechanism to keep you from catching the house on fire.
So we
With
put
the power,
we put
too much power coming
We
through.
put the microwave on a separate breaker.
Yeah, that's the way to do it.
So it's like when lightning strikes and your lights blink. It's like 'cause the lightning overloaded for a second.
Yeah, sure. And so sometimes it's enough to knock it out and blow all the breakers.
Yeah.
And sometimes you can go flip the breakers back on. If you go to the breaker box, you'll see it's turned off. It's been flipped because it got overloaded. And you can flip it back on.
Wait,
and it'll come
the
back on.
switches will flip by themselves?
Oh yeah. Yeah, it'll be flipped. Oh, you'll see it flipped. Sometimes
cool.
it's not. Sometimes it's like here's on and it's just a little off of on. Sometimes it's flipped all the way over.
Oh, okay.
Depends.
I
Yeah.
was like, those things are like you have to like like push to get.
Sometimes you have to go through all of them and see which one's tripped, right? Like that kind of thing. Did you have a question, David?
No.
Okay. All right. Let's watch a little video about electricity.
Electricity is all around us, and most of us use it every day.
We haven't seen this.
But do you really know what electricity is? To really understand electricity, you first have to start with an atom. Everything in the universe is made up of atoms. Let's look at this ant. We think of ants as being pretty small, but atoms are smaller. Much, much smaller. Atoms are so small, in fact, that one ant is made up of too many atoms to count, more than 1 billion. If you take an object and keep breaking it down to smaller units, eventually you'll be left with only atoms, which we can call the building blocks of everything. Atoms have a couple of different parts, and a really important part of an atom is called an electron. Not all atoms have the same number of electrons. The number of electrons in an atom can change because electrons can move between atoms. Electricity is the movement, or flow of electrons from one atom to another. This flow of electrons is called current, electric current. Electrons can move in all materials, but they can move through some materials better than others. If electrons can move quickly and easily in a material, then that material is a conductor. A conductor is anything that allows electric current to flow from one point to another. The opposite of a conductor is an insulator. An insulator is a material that does not let electrons move well and doesn't conduct electricity. Have you ever seen the inside of a wire? The inside is usually made up of copper or another conductive metal, while the outside is made of plastic, an insulator. The copper wire helps the electrons flow, while the plastic insulator helps keep the electricity from being wasted and prevents us from being shocked. To use electric current to power things, you have to create a complete pathway for the electric current to follow. This is called an electric circuit. An electric circuit is like a racetrack of conductive materials that let the electrons flow in a specific way. For example, let's try to light a light bulb. First, you need a power source, like a battery. Next, you need to connect wires to the battery, and finally, the light bulb. Presto! Just like that, the circuit has been completed and the light bulb lights up. To learn...
Alright, presto.
Miss Casper.
Alright, can anybody blow your balloon up?
Mine has a hole in it.
Mine making a hole. Sure.
Did you make the hole?
No.
Sure.
Alright, symbols. Symbols for circuit components. Who needs another one?
Are we doing the lab right now?
We're fixing to.
Mine has a hole also.
I have one big balloon that if we need this big balloon, I can blow this
She
one.
poked holes in them.
We have more holes? Come on.
Mine just doesn't work.
I can't. They're so small. I should have brought my little. I have this little piggy thing that
I got it.
blows thing. Oh, you got it. Yay.
Okay,
Yeah,
I got
that's
it.
something. All right. So different symbols. If you want to become an electrician, you would have to understand the symbols that would be on a blueprint of a house. And you would know that, for instance, we have diodes, capacitors, inductor, resistors, voltage, all that kind of stuff. Okay, and the last thing y'all are supposed to do is this. Conventional circuit. It turns out when they were just learning about electricity, they assumed the thing that was flowing was positive, but they were wrong. Okay, so conventional circuit, current that flows from the positive side of the battery to the negative side. This is the way the current is drawn on circuit diagrams, even though it is wrong. We know that electrons are traveling and they're going from negative to positive. All right, so I'm going to put, if you got your blanks filled in, I'm going to bring this up so you can see this. This is what you're supposed to draw. Here's the circuit, the black line. The flow is going positive charge this way, but the actual flow is going the other way, which you need to know right here that that is negative and that is positive. The big one's positive. And the small one's negative.
Oh, so this is the conventional current?
Conventional current is the red line right there. The idea that positive is flowing through a circuit instead of negative is flowing through it it's only because they were optimists and they just assumed that it was the positive that was going and not the negative. We found out later it was a negative. And you think, well, why do they still draw it in this conventional current? Because of tradition. Interestingly. Because of tradition. It's very strong, right? Tradition is strong.
Mine is
Okay, so we're going to do some lab time here, and one of the things, I'd like to try this right here. Look, check this out. The balloon.
Oh, I did a science experiment.
Did you? Can pull an aluminum can. Who's somebody have an aluminum can?
I was one of the.
There's some over there. You can buy setup.
I actually have some, my Richard's rainwater in here, but I got to drink it real quick. And the other thing we're going to do is our electroscope. I have a couple of electroscopes. What we're going to do is we're going to charge by induction. David's got it going. That's really good static for a day like today. That's pretty good. And we're going to try we're going to arrange we're not going to make an electroscope, even though your book shows a way to make one. We're going to put one together that's already made and then try to make it work. Okay? And then just at the end, happy spring. I just wanted to show you this. So, Erebus, your cat, if you want to take some balloons home, you probably can have balloons stuck to her that way.
Does it work on dogs?
If their hair is short enough and doesn't pop the balloon. Yeah. Or long enough, rather, maybe, right?
Can I have a balloon, please?
Yes. Okay. As long as we have at least a balloon blown up, then we should be able to do our
Me also, because
I do have a
my
large
husband-
balloon as well. Okay.
Probably because you